Okay, in the previous part, we saw a condition that the restricted mean curvature flow condition is reduced to an ordinary differential equation in corollary 12. That is, the evolution of the restricted mean curvature flow forms a vector field of the mean curvature vectors. In this final part, we show a way to construct invariant Lagrangian mean curvature flows in Calabian manifolds based on the previous corollary 12 with the use of generalized perpendicular symmetries of Lie groups. Here, we use a moment map, perpendicular symmetries, and a given special Lagrangian submanifold. A moment map is used to construct a Lagrangian immersion, and perpendicular symmetries and a special Lagrangian submanifold are used so that the additional condition in corollary 12 holds. Okay, first we review the conditions for the map VBC to be a Lagrangian immersion. Let M and omega be a 2n real dimensional symplectic manifold with a symplectic form omega, H a Lie group which acts on M, preserving omega with a moment map mu from M to her star, where her star is the coalgebra of her. K a closed subgroup of H, VC a submanifold of M such that VC is in MK. We suppose that the map VBC is an immersion. Then the following proposition 13 shows a condition for the immersion VBC to be a Lagrangian immersion. Under the setting star 3, suppose that the following conditions. The condition 1, the submanifold VC is isotropic. The condition 2, VC is in mu inverse C for some C in V her star. The condition 3, this equation holds. Then the immersion VBC is Lagrangian. Conversely, if an immersion VBC is connected and Lagrangian, then the map then the conditions 1, 2, and 3 hold. The condition 1 means that the symplectic form omega vanishes on the submanifold VC. The condition 2 here, please recall that the her star is the center of the coalgebra her star of the Lie group H. We call this condition the moment map condition in this talk. For the sake of the moment map condition, the immersion VBC becomes isotropic. The condition 3 is necessary and sufficient so that an isotropic immersion VBC becomes Lagrangian. Okay, roughly speaking, this proposition tells us that it is important that the submanifold VC is in the level set mu inverse C of a moment map mu, where C is a point of the center. Okay, next. As mentioned in the previous part, we would like to construct an immersion which has a nice evolution of a mean curvature vector field. That is, an evolution which forms a vector field. In order to achieve this, we use the following Lagrangian angle, which is defined on a Lagrangian submanifold in a Calabian manifold. Let M, I, G, and capital omega be a Calabian manifold with a complex structure I, a Riemannian metric G, and a Calabian structure capital omega. L, an oriented Lagrangian submanifold of M. then a function theta from L to R over 2 pi z is called a Lagrangian angle if and only if this equation holds, where a map iota from L to M is the inclusion map. Especially, a Lagrangian submanifold L is called a special Lagrangian submanifold if and only if its Lagrangian angle is constant. A Lagrangian angle is important for a mean curvature flow of a Lagrangian immersion in a Calabian manifold because the mean curvature vectors are expressed by its Lagrangian angle. The following proposition 15 tells us this fact. Let HP be a mean curvature vector of L at a point P in L. Then HP is expressed as follows. Here is the Lagrangian angle. This proposition indicates that we can consider the Lagrangian angle to be a kind of a potential function of the mean curvature vector field in Calabian manifold. Okay. Next, we show that the Lagrangian angle and the mean curvature vector of a Lagrangian immersion phi b are decomposed into two components under some conditions. We suppose the following conditions, therefore. Let mi omega and capital omega be a connected Calabian manifold, H a connected Lie group which acts on M, preserving I and omega with a moment map mu, K a closed subgroup of H such that H over K is orientable, and K preserves a Calabian structure capital omega. We see an orientable submanifold of M such that we see its mu inverse C cap mk. We suppose that the map phi bc is a Lagrangian immersion. Then the following proposition 16 holds. The claim 1, the Lagrangian angle theta c of the Lagrangian immersion phi bc is decomposed into the following two functions. The function theta h depends on only the h action, and the function theta bc depends on only a position p of the submanifold bc. In fact, the Lagrangian angle theta c at a point hkp is determined by the value of the function theta h at a point hk, and the value of the function theta bc at a point p. Okay, we note that the function theta h is defined only by m, h, and k. Especially, theta h is independent on bc. Okay, and the claim 2, since the mean curvature vectors are expressed by its Lagrangian angle, so the same thing holds for the mean curvature vectors. That is, the mean curvature vector hc of the immersion phi bc is decomposed into the following two components. Here, the first part, AH, is a vector field which is defined only by M, H, and K. And the second part is determined only by a position P on the submanifold BC. Okay, roughly speaking, the proposition 16 tells us the mean curvature vectors HC of the immersion PBC can be decomposed into the curvature of the submanifold BC. Submanifold BC and the curvature AH of the orbit, which is formed by a Lie group action. What is especially pleasing here is that the first component AH forms a vector field on MK. We aim to make this vector field AH the vector field A in the previous corollary 12. For that, we need to erase the second part. That is, we make a situation in which the function theta bc is constant. In order to achieve this, we use a given special Lagrangian submanifold L and a perpendicular action to L as follows. We suppose the following setting star 5. Let Mi, omega, and capital omega be a connected Cavier manifold, H a connected Lie group which acts on M, preserving I and omega with a moment map mu, K a closed subgroup of H such that H over K is orientable, and K preserves capital omega. AH a vector field along MK as in proposition 16. L a special Lagrangian submanifold with Lagrangian angle theta, which is constant. C is in Z har star, the center of the coalgebra. BC and N minus the dimension of H over K dimensional submanifold of M, such that BC is in mu inverse C cap LK. Okay, first we note that here, under the setting star 5, the immersion phi BC. The immersion phi BC is a Lagrangian because it is in the level set of a moment map. Okay, then the proposition 17 holds. Under the setting star 5, suppose the following condition, where C sharp is the fundamental vector field with respect to the H action. We call this condition the generalized perpendicular condition. We explain this using the following figure. This condition indicates that for any point P in BC, the fundamental vector field C sharp P is perpendicular to L. The previous strictly perpendicular condition in the result of Professor Konno requires that the H action is exactly perpendicular to L, like this arrow. On the other hand, the generalized perpendicular condition allows the H action having a component of the direction of VC, like this arrow. Okay, either way, the image of the immersion phi BC is perpendicular to L. Okay, then it holds that the claim 1, the function theta VC becomes constant as we intend. Here, theta is a Lagrangian angle of the given submanifold L. This is as if the curvature of VC in the given submanifold L is copied in the perpendicular direction. Okay, as a result of the claim 1, the claim 2 holds. That is, the mean curvature vector HC of the immersion phi BC coincides with the vector field AH of the submanifold VC, as we also intended. To our delight here, the vector field AH actually runs along the special Lagrangian submanifold L. So the submanifold VC stay in the special Lagrangian submanifold L by the deformation generated by the vector field AH. The next moment. Hence, the situation of proposition 17 will be reproduced continuously. That is, the restricted mean curvature flow of the submanifold VC is written by the vector field AH. This fits the situation of the corollary 12. Therefore, we can obtain a Lagrangian mean curvature flow of the immersion phi BC by calculating the deformation of BC and expanding it with the use of perpendicular action. Okay, consequently, we obtain the following main theorem 18. Under the setting star 5, suppose that the vector field AH generates a deformation small f of VC with its expansion capital F. And for any time t in 0t and vt, which is defined by FTBC, the generalized perpendicular condition holds. Then the vector field AH and vt for any time t satisfies the condition of corollary 12. And the maps FT are a Lagrangian mean curvature flow of the Lagrangian immersion phi BC. Okay, at the end of this talk, we introduce some examples of our method in the complex Euclidean space. The first example is a Lagrangian self-similar solution in C4. This is constructed by a strictly perpendicular symmetries of a non-abelian Lie group U1 cross SO3. A second example is a Lagrangian mean curvature flow in C5 using generalized perpendicular symmetries of an abelian Lie group U1 cross SO2. A third example is a Lagrangian translating soliton in C5 using strictly perpendicular symmetries of a non-abelian Lie group R cross SO3. A fourth example is a Lagrangian translating soliton in C6 using generalized perpendicular symmetries of an abelian Lie group R cross SO2. These are our examples. The first and second examples are generalizations of ones by Lie and Wan in 2010. The third and fourth examples are generalizations of ones by Castoro and Lerman in 2012. And all examples can be considered as generalizations of examples by Connor in 2018. Okay, that's all for my lecture video. Thank you very much for your watching.